Range, 5,500 nautical miles. Target coverage, 100% of major industrial targets. Speed at impact, about Mach 6. Circle of probable error, 1,500 feet. Payload, 3,000-pound bomb, atomic type. Here is a typical Atlas launching site, as it would appear on an operations base located within the continental United States. Each Atlas base, as presently conceived, consists of some 10 of these launching sites, with their associated installations, command and support facilities, and downrange guidance stations. The surface-to-surface missile is a pilotless rocket-propelled spacecraft. It is 12 feet in diameter and stands 110 feet high. The fabricated weight, representing the major cost, is 22,000 pounds. The launching weight is 440,000 pounds, of which 409,000 pounds are propellants. The three major sections of the missile are the warhead, the body or tank section, and the propulsion section. Main propulsion is furnished by 5 existing 120,000-pound thrust rocket motors, now being converted from alcohol liquid oxygen to gasoline liquid oxygen in order to improve the specific impulse and simplify logistics. The 4 outer motors are rigidly mounted in a booster unit, which is dropped after about 2 minutes of flight, leaving the center motor to provide sustaining propulsion for another 2 or 3 minutes. This is known as the 1 1/2 staging technique, and has the important advantage of permitting all motors to be started on the ground. The center motor is gimbal mounted and swiveled to achieve directional control in pitch and yaw. The 2 small vernier rockets provide roll control, and also, after the sustainer motor has been cut off, they furnish the delicate velocity and directional adjustment required just before final power cutoff. Because no tankage is jettisoned at the end of the booster stage of propulsion, it is desirable that the tanks weigh as little as possible. This is achieved with a simple monocoque body structure consisting of 2 integral thin-gauge stainless steel tanks with no stiffening of any kind, except by internal pressure. All equipment on the body section is mounted externally in 4 longitudinal pods, where it is most accessible. 2 of the pods are liquid oxygen lines on which the vernier rockets are mounted, and the other 2 house all the electronic gear, including the transponder, the program timer, the integrating accelerometer, and the autopilot gyro units and their circuitry and power supplies. The chief components of the 7,200-pound Warhead are the 3,000-pound bomb, the stabilization equipment, and the provisions for protection against the tremendous heat flux on the skin surfaces caused by aerodynamic heating upon re-entry to the atmosphere. Since the warhead contains the entire payload, it is the only part of the missile which must be delivered intact at the target, and is therefore separated from the rest of the missile immediately after power cutoff. From this point, it sails like a boulder flung from a gigantic catapult in a free fall through space until it re-enters the atmosphere over the target on the other side of the Earth. Thus, Atlas is a ballistic weapon, and the warhead, in the ballistic sense, is actually the missile, while the body and the propulsion sections jointly are the ballista, or catapult that hurls it at the target. Looked at another way, the Atlas missile may be seen as a spacecraft that drops its bomb from an altitude of some 115 nautical miles at a speed of about 14,000 knots to hit a target on the other side of the world. With such a range, it is obvious that the Atlas guidance system, though it need function only during the catapult or powered phase of the missile flight, must be extremely precise. This precision is achieved by combining the inertial guidance method, which relies on the autopilot, programmer, and integrating accelerometer in the missile, with the precision of the ground supervision principle, employing a precise phase comparison tracking system, a digital computer, and a command control link with the missile. This composite system, known as a ground supervised inertial guidance system, completes its entire function within some 5 minutes of launching, while the missile is still over friendly territory, making the jamming of its signals by the enemy extremely difficult. The ground-based components, which comprise about 98% of the entire system, are all located together in a stationary guidance station some 200 miles downrange from the launching site. And as an additional reliability measure, several of these guidance installations may serve each operations base, any one of which may be used in directing any missile launched from the base. The missile is launched vertically and initially directed by the programmed autopilot. As it rises above the radio horizon of the guidance station, tracking begins, followed shortly by ground supervision through the command control link to the autopilot. The purpose is not to confine the missile to a predetermined flight path, but to continuously adjust the observed velocity vector of the missile, V sub m, toward the required final velocity vector, or aim at cutoff, V sub r, which is continuously predicted from the missile's observed track at each instant. As noted before, guidance ends at power cutoff, within some 5 minutes of launching, at an altitude of around 115 nautical miles. Here, the warhead is automatically separated and armed to complete the remainder of the 30-minute flight in a high vacuum along a Kepler ellipse with the utter reliability of celestial mechanics. At the apogee of such an orbit, it attains an altitude of over 500 nautical miles. Some 15 minutes later, and only 20 seconds from impact, it re-enters the sensible atmosphere at a speed of about 14,000 knots. This is well above what the aerodynamicists have termed the heat barrier, the effects of which can be observed on almost any clear night. In terms of the Atlas warhead design, it means possible skin temperatures of 10,000 degrees Fahrenheit and heat fluxes of 25 million BTU per square foot per hour. This heat barrier has been attacked by several task groups of scientists with a whole battery of weapons from the scientific arsenal. The physicist and the dynamicist have teamed to develop the stabilization or attitude control mechanism, which employs an inertial gyro and two space wheels to orient the warhead into a nose-first re-entry attitude, thus greatly reducing its aerodynamic loading. Here we see a full-scale laboratory model of this robot directing the suspended warhead model into a preset arbitrary attitude. Note that it is undeterred by any sort of outside disturbance. The design engineer and the aerodynamicist have teamed to develop a warhead configuration with sufficient drag in the thinner upper layers of atmosphere to slow its speed before it reaches the denser lower layers, but not so much that the wind drift is excessive or the Mach 6 impact velocity impaired. This team is also making extensive use of various high-speed wind tunnels to determine the air form that will produce the least turbulence in the denser atmosphere. The thermodynamicist and the chemist have teamed to discover the most efficient heat-absorbent materials for use in insulating the surface of the warhead. In this search, they are using several especially constructed tools, such as this Convair solar furnace, in which small specimens of ceramics, metals, and ceramets are heated as high as 6,000 degrees Fahrenheit by concentrating a 10-foot circle of the sun's rays on a 3/8-inch focal spot. Other such tools include this hydrogen-oxygen wind tunnel built by a subcontractor to test materials in a rocket blast with velocities up to 6,500 knots and temperatures up to 6,000 degrees Fahrenheit. And this light gas gun at the Naval Ordnance Test Station in Yukon, California, which is designed to fire half-inch pellets through a 75-foot air chamber at velocities up to 8,800 knots. One of the most promising assaults on the heat barrier is being made by the thermodynamicist with an adaptation of the familiar sweat cooling process of the human body. In this technique, known as transpiration cooling, a fluid such as water is forced under pressure into the pores of a porous metal skin, where it is converted by aerodynamic heating into superheated steam, which carries off the heat into the atmosphere. During the test we see here, in which a specimen of composite skin material made by copper plating large pore sintered stainless steel was heated by electrical resistance, a heat transfer rate of 14 million BTU per hour per square foot was achieved. To appreciate the implications of this, compare it with the 6 to 10 million BTU per hour per square foot heat transfer rate at the throat of this Atlas rocket motor, or the 130,000 BTU per hour per square foot capacity of this modern steam power plant. However promising such laboratory experiments may be, they cannot be considered conclusive until some of the unknowns of the hitherto unexplored Atlas tactical environment are determined in flight. To this end, the so-called Plan 4 development program for the Atlas project has been adopted in order to provide two simpler and cheaper flight test vehicles with a minimum of additional design and development effort. Both flight test vehicles will have the same basic airframe and rocket motor design as the XB-65 operational prototype missile that we have been examining. The first test vehicle to be built, the X-11, will be propelled by a single 120,000-pound thrust rocket motor, gimbal for directional control, and otherwise similar to the center motor of the XB-65, except for the shorter nozzle, and alcohol as fuel instead of gasoline. It will also carry a 1,200-pound instrumented test nose instead of the 7,200-pound Warhead. Tested over a 150 nautical mile range and attaining a maximum altitude of 330 miles, it will be capable of exploring re-entry conditions at about 6,000 knots, as well as proving basic airframe and equipment design. The second test vehicle, the X-12, is achieved by adding two 120,000-pound thrust alcohol liquid oxygen motors and their accessories as a stage booster unit, and substituting a 1,600-pound separable test nose. Tested over a range of about 1,400 nautical miles, the instrumented nose will re-enter at close to operational velocities, and instrumentation on the body section will provide data on the 1 1/2 staging operation. The prototype guidance system will be used to guide all test flights, and all test data will be directly applicable to the design of the XB-65 operational missile. The XB-65 will differ from its immediate predecessor, the X-12, mainly by the extension of the rocket motor nozzles, the addition of two more rocket motors to the booster unit, the use of gasoline as fuel, and the substitution of the 7,200-pound Warhead in place of the test nose. Since the basic rocket motor and airframe design are the same for all missiles of the Plan 4 program, we may consider the following development activity on these components and their accessories as equally applicable to all three versions. As may be seen here, the conversion of the 120,000-pound thrust rocket motors from alcohol locks to gasoline locks is progressing satisfactorily. The thrust chambers of hydroformed lightweight tubing assembled around a jig fixture are identical in all of these motors, except for the extended nozzles of the XB-65 motors for increased efficiency at high altitudes. The rocket test program now underway at the Santa Susana Field Laboratory will prove such developments as the gimbal mounting of the center motor, as well as the complete rocket assembly package. On one of the gasoline locks tests already run, a converted motor delivered a thrust of 131,500 pounds for 39 seconds. And this duration was limited only by the capacity of the test stand's propellant tanks. A specific impulse within a few percent of design requirements has been achieved with the JP4 fuel. Convair is contributing to propulsion development with such accessories as this mixture control system to ensure maximum utilization of propellants. The system is to assure a residual propellant weight of not more than 700 pounds at final power cutoff. The contractor is also developing a high-stability servo system to swivel the large mass of the central motor in response to autopilot signals. A mock-up of this system is here being used to obtain experimental verification of performance predictions made by dynamic analysis. The heavy pendulum represents the rocket motor mass. The hydraulic actuator may be seen displacing the pendulum in response to the signals imposed by the operator. The servo valve, which converts the electrical impulses from the autopilot into hydraulic impulses to the actuator, is here being tested to determine its performance characteristics. To determine the closed-loop stability characteristics of the servo system in the laboratory, it was necessary to build this dynamic simulator. It automatically simulates electronically the missile movements in response to rocket motor displacements. The autopilot gyro and signal amplifier elements are of conventional design and operation. Since the dynamic frequencies of the autopilot system couple with the rigidity and vibration characteristics of the body structure, knowledge of these characteristics is very important. Hence, a stainless steel pressurized model of the propellant tanks was constructed and vibration tested in this explosion-proof tower. Results agreed very closely with theoretical prediction. Both dynamic and static characteristics of the body structure will be explored through exhaustive vertical and horizontal loading and operating test of a full-scale tank section and its accessories in a test arrangement to be built in San Diego. This scale model of the test arrangement shows how the tank section, which has been subcontracted for delivery in August 1954, will be installed and erected to the vertical position. The test tower will be 115 feet high. The joints in the tank structure must maintain their structural efficiency over a wide temperature range, while pressurized up to 80 pounds per square inch. Structural tests like this were conducted on a great many riveted and adhesively bonded joints in aluminum alloy sheet, and on welded joints in stainless steel sheet, at temperatures ranging from minus 320 degrees to plus 350 degrees Fahrenheit. The .035 gauge Type 301 stainless steel seen here under tension test at high temperatures demonstrated a strength in 30 specimens of nearly 98% of the strength of the parent material over the entire temperature range, and the welded joints proved to have the required tightness. As a result of these tests and analytical studies, stainless steel was selected for the airframe construction. To establish the aerodynamic characteristics of the various possible body configurations, numerous wind tunnel tests were conducted at Mach numbers up to 10. In this Schlieren test run at Mach 2.17, the familiar configuration with the 4 external pods was moved through angles of attack from minus 10 to plus 10. Development activity on the missile-borne guidance components, in addition to the work on the autopilot servo system, has included improvement of the power output of the transponder by such means as these overrating power tests on the SAC-9 Klystron power tube, using various cooling methods. During one air-cooled test, the tube operated for 4 hours at 5 times its rated output. The major effort on the ground guidance components has been devoted to testing, evaluating, and refining to Atlas requirements the Azusa phase comparison tracking system previously developed by Convair under Air Force sponsorship. After successfully completing its acceptance tests at San Diego, the Azusa system was delivered in August 1953 to the Air Force Missile Test Center at Cape Canaveral, Florida, where we see the antenna baseline being installed. By tracking airplane and missile flights at Cape Canaveral, the contractor will gather additional data for use in developing the Atlas tracking system. Meanwhile, this Atlas antenna has been designed to incorporate several refinements, including a gimbal mounting that permits a full 180 degrees of elevation through a full 360 degrees of azimuth. These refinements have involved the development of the improved waveguide rotary joint, shown here being mounted in an Atlas antenna yoke bearing, and also the development of cable leads capable of continuous reciprocal twisting through large rotation angles without fatigue. Other antenna developments include this improved nutating feed method, these heavy base plates capable of micrometer adjustments, and these extremely rigid antenna pedestals. This microwave phase meter was especially designed and fabricated for use in refining the Atlas tracking circuit phase stability. And this special equipment to determine computer system logic and calculation speed requirements in defining the Atlas guidance computer specifications. It is expected that a commercially available digital computer such as this IBM 701 will be capable of meeting the definitive specifications when established. Major development effort on the command control unit has been directed toward determination of the optimum command control method. When all of these ground components of the guidance system, the complete tracking unit, the digital computer, and the command control unit are assembled and installed in the Atlas guidance station, it will look something like this, with the tracking antenna probably housed under radomes on the roof. In order to see how the whole weapon system works, let's follow the XB-65 from its assembly at the operations base through an operational launching and flight to its destination on the other side of the Earth. These mating cradles also serve as transport trailers for their respective components. Now the entire missile rests in the body cradle, which is a combination trailer and work stand. After being towed from the assembly building to the nearby launching site, the trailer is assembled to the launcher and erected on the launcher along with the missile. One of the reasons for this is obvious if we remember that the 75-foot tank structure has nothing to stiffen it except the pressure in its tanks. Another purpose is to employ the built-in elevators that run the length of the trailer as working platforms for pre-flight preparation of the missile. After these preparations have been completed, including starting and monitoring the transponder signal, the trailer work stand is lowered and hauled clear. Now all of the rocket motors, including the verniers, are ignited. And after they have all been observed to be operating satisfactorily on pre-stage, the main stage of all motors is cut in automatically.
Firing circuit on. Programmer. Pressurization. Ignition. Pre-stage. Main stage.
When thrust reaches the required figure, the missile automatically releases the hold-down latches and begins to rise at an acceleration of 1/2 G. For the first 10 seconds, it is guided in a vertical ascent by the autopilot alone, acting through the servo system to swivel the central rocket motor. At about 1,000 feet, the programmer directs the missile by means of the autopilot away from the vertical and into its trajectory. The transponder is emitting its continuous 5,000 megacycle signal. As the missile reaches about 60,000 feet altitude, it rises above the radio horizon of the guidance station, and the tracking system picks up the transponder signal from the missile, locks on, and begins to track. Continuous position data from the tracker is fed into the digital computer. During the next minute, as tracking continues, propellant expenditure reduces the missile weight to the point where the booster motor thrust is no longer needed to maintain the desired acceleration. At this point, the programmer jettisons the booster unit, leaving the gimbal sustainer motor and the verniers to continue furnishing propulsion. The acceleration drops from 6 to 1 G and gradually starts building up again. A few seconds later, at about 200,000 feet altitude, the missile emerges from the sensible atmosphere and the command control phase of guidance begins. From the continuous position data furnished by the tracking system, the computer continuously computes the velocity vector of the missile and compares it with the required final cutoff velocity vector, or aim, for the observed track at each instant. The vector adjustment is transmitted through the command control channel to the autopilot as a missile heading correction and to the accelerometer as a cutoff velocity correction. The autopilot adjusts the heading by swiveling the sustainer motor. As the power cutoff point is approached, the integrating accelerometer cuts off the sustainer motor at a few feet per second less than the last signal cutoff velocity. The final precise velocity increment, within a fraction of a foot per second, is thus provided by the two small vernier rockets, which are then cut off by the accelerometer, terminating powered flight and guidance simultaneously within some 5 minutes of launching. Immediately thereafter, the warhead is automatically separated from the body, and the bomb is then armed. The stabilizer, through the action of its space wheels, compensates for any separation disturbances and begins to slowly orient the warhead toward its nose-first re-entry attitude. The Warhead is now coasting toward the apogee of its trajectory, decelerating somewhat under the pull of gravity, while the body of the missile falls slowly behind under the effect of the additional deceleration imparted to it at separation by the release of the pressure from its tanks. From the apogee of its elliptical orbit, about 500 miles above the Earth, the Warhead accelerates in its long plunge toward the target until its speed as it re-enters the atmosphere is about the same as at separation, close to 4 nautical miles per second. The temperature on the nose is about 500 degrees Fahrenheit and rising rapidly. The huge empty tank section is still trailing close behind, an effective radar decoy. Radar might pick up either now, but it's too late. It's just 15 seconds to impact. Speed, Mach 6. Range, 5,500 nautical miles. Flight time, 32 minutes.